Hello, my name is Mohammad Osama. I am a PhD fellow at Information Technology University, Pakistan. Today I am going to present my paper, Adversarial Attacks on Cognitive Self-Organizing Networks, the Challenge and the Way Forward. My co-authors on this paper are Dr. Junaid Qadir and Dr. Ala Al-Fuqaha. During the course of this presentation, I'll follow the following outline. First, I'll tell you about the motivation and the problem. Then I'll tell you about methodology for adversarial attacks on CSONs. Then we'll talk about the results and few open issues. So first I'll tell you about the problem and the motivation. Cognitive self-organizing networks addresses the challenge for network operation that arises due to complexity, heterogeneity, and diversity of, of the networks. And CSON are intended to solve these problems by building AI-based optimization, healing, protection, and coordination algorithms. And by building these algorithms, CSONs are expected to improve the network coverage and capacity by reducing the operational expenses and ensuring steady state of security. Application of machine learning in CSONs are very critical, and a lot of research is coming out based on machine learning algorithms application in networking. Few of them are knowledge-defined networking, where a knowledge plane is proposed on over SDN, and which gets data from analytics platform and use machine learning algorithms to learn the parameter of SDN controller. Similarly, network telemetry data and service KPIs are used for learning the control parameters, and this paradigm is called data-driven networking. Similarly, deep reinforcement learning-based network policy learner is also known as experience-based networking. So, to summarize this, recent advances in neural networks and computational technologies have made machine learning a popular choice for building intelligence in networking. Since we are using machine learning in the networks, it comes with its problem. We have problems with physical domains, and we know how to deal them. We have problem in digital representation, and we have learned over time how to deal with that. But since we are applying machine learning to this stack, machine learning comes with its own problems also, and this will add another threat layer. And the problem that I am talking about is known as adversarial perturbations. Adversarial examples are carefully crafted perturbations in the input which forces machine learning algorithms to malfunction and yield wrong classification and prediction with very high probability, and that can actually make machine learning a very dangerous tool to use in CSON without taking appropriate care. Through this paper, we intend to answer following questions. Number one, we intend to look into the robustness of machine learning for CSONs, and then we'll talk about the deterrence building in CSONs, and then we'll look at the arms race between adversaries that will occur due to the application of machine learning and deterrence techniques against adversarial examples in CSONs. Through this paper, we want to make following contribution. First, to the best of our knowledge, we are the first one to make an attempt to show that CSON utilizing machine learning techniques are very vulnerable to attacks based on adversarial perturbation. We have also argued that existing defenses are not good enough for CSON or networking applications. We have also highlighted the threat of arms race between adversaries using machine learning algorithms. Now I'll talk about the methodology for adversarial attacks on CSON. First, I'll talk about the threat model that we have used. We have considered white box setting, which assumes that adversary know about the model architecture, hyperparameters, cost function, and training data. We have only considered evasion attacks. We have not considered poisoning in this paper. We have also taken security to encompass the functional area of CSON, and in security we have only considered malware classification, but these attacks works on any kind of classification perturbation or classification prediction or policy learning algorithm. The goal of the adversarial ML attacks is to actually compromise the integrity of the deployed ML based networking technique. Since there does not exist any standardized machine learning based malware classification model, so we took the liberty of designing our own. We have proposed a convolution neural network based malware classification model where we have utilized malware image dataset, which is a very highly cited malware image dataset, and then we have used when we have achieved state of the art 98.39% of accuracy on 25 class problem, we have used three two-dimensional convolutional layers and a dense layer with softmax function to collect the classification probabilities. We have considered malware classification as a proxy example, as I told you earlier, and we have performed three adversarial attacks: fast gradient sign method, basic iterative method, and Jacobian based saliency map attack. So in fast gradient sign method, we perform one step gradient update along the sign of the gradient to solve the optimization problem. Formally, the perturbation is calculated as a gradient with respect to the input, and then we look for the sign and we perform perturbation in that direction. So this perturbation is added to the input sample, and this will yield a adversarial example which, when subjected to the classifier, produces false classification results. Basic iterative method is improving the success of FGSM by iteratively applying it with smaller step size for generating adversarial example for physical words. So it is nothing but the application of FGSM iteratively, and this will produce iterative adversarial example. Rest of the settings are similar to FGSM attack. Thirdly, Jacobian based saliency map attack. This attack is an iterative method of generating saliency map. So this attack generates a saliency map of malware data, and through that map we can get the most discriminant features in that in the malware data, and by adding a heuristic based perturbation to those discriminant features, we force the classifier to misclassify. We have also looked on the available adversarial defenses. So number one was adversarial training, where we add adversarial example to training data and train a model on that to secure our model from adversarial threat. But this defense only works when you know the adversarial example. Secondly, network distillation. This defense is based on hiding the gradient between pre-softmax layers and softmax output, which reduces the chance of developing a gradient-based attacks against deep neural networks or deep machine learning techniques. Now I'll talk about results and discussions. So firstly, we'll talk about the results of FGSM attack on malware classification before and after adversarial training. So test accuracy. So once we have trained the model, we have like 98.39% accurate model. But once we have performed the FGSM attack, we have seen a decrease of classification accuracy of 97%. So the classifier is not even able to detect more than 2% accurately, or detect or classify, or actually the test accuracy after adversarial training is actually telling that when we have included adversarial example and we have included adversarial example and training data, and we have trained the model on that, and then we have calculated the accuracy against adversarial example. We were able to get nearly 80% of the accuracy, and which tells that by using adversarial training we can actually improve the defense of a machine learning based model. But still this accuracy is not acceptable uh, given the given the sensitivity of CSONs. Then we have performed BIM attacks, as I mentioned earlier. So this attacks also destroys the machine learning algorithm. So we have like a machine learning algorithm which was giving a classification accuracy of 98% nearly. Was Once we have performed this BIM attacks, we have faced a loss of accuracy of 96%, and when we have performed adversarial training, we have improved from 0.90 to 61%, but this is still not acceptable for CSO and standards. Then we have performed JSMA attacks. So JSMA attack is producing state-of-the-art adversarial examples for vision and language processing, but for network data, for malware data, actually this does not work, and this was a very unusual result. Uh, since we have a model trained and nearly producing 96 or 97% accuracy on legitimate samples, once we have performed this attack, we have faced the loss of 85% of accuracy, but we have to perturb nearly 90% of the features, which is like changing the whole data. So that is why I'm saying that for this data set in consideration, this attack does not work. So we set out to answer three questions in the beginning. So first question was the robustness of ML and DL for CSONs, and our results highlighted that the current machine learning schemes are not able to provide any deterrence against adversarial ML attacks. Second question was deterrence against adversarial attacks in CSONs. So our results also highlighted that existing defenses are not good enough for providing a valuable defense against adversarial attacks. And then we have also highlighted that both parties will be using both adversaries will be using machine learning algorithms. So this will create another arms race in networks, and networking community has to come up with a solution or a trade-off for dealing with this arms race between adversaries. During these experimentations, we have also noticed few open issues. First open issues was standardized data set. We don't have standardized data set to perform experimentations to come up with a proper robust ML algorithms for networking. Secondly, we have waste a lot of network data. We only learn from metadata and headers. So this is not appropriate. We need to learn from untapped network data in order to make more efficient and more effective and more robust machine learning model for networks. And we as a networking community has to come up with uh, by including the domain knowledge, we have to come up with models, machine learning based models that are very specific to networking data and networking examples. So these are few open issues that we have seen during these experimentations. So concluding remarks are: we demonstrated that network data is highly susceptible to adversarial attacks, and we have also highlighted that machine learning may push the limits on the state of the art in CSONs, but uh, without taking into account that threat of adversarial examples, significant security risk will be major hindrance to the deployment of these networks. I have included I have used following references for making this presentation. Uh, Thank you very much for listening. Please feel free to email me if you have any question. and thank you very much.